And it's a great pleasure for me to introduce my colleague, Tom Spencer from the School of Math. He's worked on statistical physics, every type of aspect of it, from percolation to random Schrodinger and absolutely to random matrix theory. And that's the title of his talk. And he, I think, give us an exposition of this topic, statistical mechanics arising from random matrices. Thanks.
Thank you very much, Peter. So it's I want to thank the organizers for this invitation to speak at a conference which looks like it's going to be very lively. And when I came up this morning, there was seemed to be so much activity and interaction. I look forward to the following days. We've already heard really inspiring talks by Peter and by Hugh and by John. So for me, I want to start out by saying, for me, the connection between random matrices and Riemann zeta, pioneered by Montgomery and by Dyson, is one of the most fascinating puzzles in mathematics today. It still is. We have some progress, but there's so much more to be done that we don't understand, certainly at a very precise mathematical level. You know, when one of the things that I have learned about recently, which I will mention, is that there's some simple random matrices which you can write down, and you can say, well, do they have GOE or do they have GUE statistics? And numerics will show you one thing, and what you can prove is something entirely different, of course. So although a detailed properties of GOE and GUE matrices, they've been well understood for over 60 years. So the goal of this talk today is to examine other models which come from mathematics and physics and see what progress we've been able to make on them. And these include things like random band matrices, random Schrodinger, and quantization of chaotic systems. There are numerous numerical and theoretical results, but a lot of it is still speculation from a mathematical point of view. So let me start I will begin with a review of theorems and conjectures about random matrix theory. We want to understand how universal these properties are. We see them in Riemann zeta, we see them in many other systems, but what can we actually prove about specific random matrix ensembles? So part two of the talk will concern more the connections with statistical mechanics. So most of you here are not so familiar with statistical mechanics, but the way to think about it, if you like, is as an integral representation for various quantities that you might want to understand in random matrix theory, pair correlations, this kind of thing. So there are integral representations, but these integral representations are fairly complicated, and they involve not just one integral, but involve an integral with many, many variables. And that's what statistical mechanics is about. So, so the first person to really pioneer this direction was Franz Wigner around 1980, and he invented what he called the hyperbolic sigma model. We'll see why hyperbolic symmetry plays a crucial role in some of the things that arise today. And then later, so he used what are called replicas, which are commonly used in disordered systems, but these are not rigorous, but he certainly inspired a lot of activity in the area of statistical mechanics and trying to understand its connection with random matrix theory, random Schrodinger, and other operators. So then Konstantin Efetov, around 682, he made up a model which is rigorous, there's a rigorous equivalence between random matrix theory and these models. They're supersymmetric. And they have what here I've indicated a U1,1/2. So you don't really have to know what that means, but the 1,1 means hyperbolic, and the 2 stands for an SU2 symmetry that sits behind these things. So these models have a lot of symmetry in them, and that makes them very interesting. It also makes them hard to analyze. So these things, I consider these representations of supersymmetric statistical mechanics as being a kind of non-abelian Fourier transform. or it's a kind of duality. It's another way of thinking about the same problem, but with different perspective. You can use, for example, you can use stationary phase, or you can use steepest descent. You can use renormalization group ideas. And these are ideas which are not so common in the ordinary random matrix community. So now let me start very briefly with reminding you about Gaussian unitary ensemble. I know most of you know this very well, but I thought just for completeness, I would start by giving more precise statements. So here we have an n by n complex matrix. It has Gaussian distribution, and the average of the matrix elements are 0, but the entries are independent, except that this Hij bar has to be 1 upon n. So the 1 upon n is just a scaling factor. All matrix elements have equal weight, and they're independent. And this is the relation that you can think of, or equivalently, you can think about it with this trace weight. So if we look at the eigenvalues of the random matrix, which was really studied by Godin and Mehta, Dyson, the spectrum runs from -2 to 2 in this representation. And we have what we have to look at, however, if we want something universal, we want to understand something that looks like the zeros of Riemann zeta or other systems, we have to rescale the spacings. And you rescale them by the average spacing, the average typical spacing. Because if I change things by a factor, I want something to be invariant. And if I divide by the spacing, which is what I have here, this is the average spacing, then what I'm doing is I'm taking the eigenvalues, which are very close, and I'm blowing them up so the distance is of order unity typically. And then we're interested in the fluctuations. So this average spacing near an energy level E is just given by the density of states. This is the Wigner semicircle law, and then times n, which is the size of my matrix. So that's the rescale spacing, which is supposed to be observed to be universal in the case of unitary ensembles. In other words, those which are not, which have, let's say, a magnetic field, or you have complex entries in the matrix. So then, of course, there's the famous, we saw it today in Hughes' talk, the famous pair correlation, and which I'll write out here. That's just the probability of finding 2 eigenvalues rescaled at some distance. And there are also exact expressions for GOE and GSE, the symplectic ensembles, but these are different. They have different properties. They have different statistics associated with them. So the Wigner and Dyson universality really starts with Wigner, and then Dyson really makes it precise. And I think Mehta is very much involved with this. Says that as n goes to infinity, these eigenvalues, these lambda k's, should be the same for many complex systems. Not everyone, but many complex systems have this symmetry. So we try to have these statistics, rather. So we try to understand how this happens and how the symmetry enters, and so crucially. So here I have to say that the eigenvalues have to be kept away from the edges of the spectrum. Otherwise, you'll see other statistics. So this is seen, and we'll go through many of the models which one expects to see this phenomenon. So one of the first ones I want to mention, which is already much more difficult to understand than the GUE matrices. They're very similar, but there's a difference. And these are random band matrices. And these have a spatial structure. So I and J now are not indexed by 1 to n. They belong to a d-dimensional lattice. And we look at the lattice and we look at a box inside that lattice. So we're going to make the box go to infinity. That's going to be like large n matrices. So this is the box of side n. So if we were doing this in 1 dimension, this would be similar, but not the same as GUE. But the point is that the JIJs here are important, and the band means is that they have a width. So if I minus j is bigger than W, so W is some fixed number, maybe quite large, then the JIJs are small. So that means you have a matrix which is not complete. It has zeros outside of a band of width W in one dimension. That's the way to picture it. And we've normalized it so that the JIJs, if I sum over the JIJs, I get 1. So that's just a normalization. So the spectrum still runs between -2 and 2 as it did before. And so Wigner also studied band matrices, by the way. I didn't realize this until recently. He did this in one dimension, and he called them bordered matrices. He had maybe some extra weight along the diagonal, but he was also interested in these matrices. Now, there's a prediction due to Jan Fyodorov, who's here, and Sasha Mirlin, that in D equals 1, we get GUE statistics provided that the width is bigger than the square root of n, much bigger than the square root of n. And this is one of the cases where statistical mechanics have been quite useful. This has been proved, a special case has been proved by Maria Sherbina and Tanya Sherbina, her daughter, using supersymmetric statistical mechanics. Okay, I won't go too much into detail about this, but I will explain some simpler question which they've also studied. And by the way, this is a sharp result. The GUE statistics fail if the width is too small, is less than the square root of n. So there's earlier work by very different methods due to Bourgade and Yao and Yin, and here they require W bigger than n to the 3/4, and they're using more conventional techniques which have been around for longer. But as far as I know, they cannot reach this end of the half, which the Sherbinas have done. So this is an example of where you have GUE, but you have to have conditions on the matrix. You have to have it has to be wide enough, can't be too narrow, for example. So that's an example of a simple example. So now let me just give you I guess a survey of where we know something. We know quite a bit about the local statistics. So the pair correlations or the spacings, and so the first one to mention is what are called the unitary invariant ensembles. So the weights are now given by the trace of a polynomial of the Hamiltonian. And so we can take px to the 4th, for GUE, we take x squared, but this was done, this is a very interesting ensembles. One can study it for many different weights. They're also very interesting in physics. So this was done using orthogonal polynomials by Deift, Itz, and Giov, and then also by Pasteur and Sherbina. So this is where orthogonal polynomials arise, and Riemann-Hilbert methods are used. It's a very rich area. The second ensemble of matrices are called Wigner matrices, and these are mean field. They're like the GUE or GOE, but they're not necessarily Gaussian. The matrix entries can be plus or minus 1, or they could have some other distribution. And here is where Freeman-Dyson comes in. So this is a very interesting story, which those of you who have heard Yao speak, you know something about it, because this is the technique that he's really uses very heavily. So to understand why you see universality in these Wigner matrices and other matrices as well, he takes the matrix and he lets it flow under what's called Dyson-Brownian motion. If you let it flow under Dyson-Brownian motion, this is a Gaussian process, and it will converge to GUE. And the amazing thing is I think they learned this from Dyson, is that the convergence is very, very rapid. The local energy levels converge extremely rapidly. So a very fast local equilibration of eigenvalues in time 1 upon n. So you let it flow, you don't get global equilibration, but you get local equilibration very rapidly, and that's what they prove. And here's Dyson's quote. The picture of a gas, so the gas here he's thinking about are the eigenvalues of the matrix, interacting by a log potential, because that's the effective weight, coming into equilibrium in two well-separated stages with microscopic and macroscopic timescales is suggested with the help of physical intuition. So he knew right away this is what was going to happen. It was going to be a short time for local equilibration, long time for global equilibration. And a rigorous proof of this picture, that this picture is accurate, would require a much deeper understanding. And that's what Yao and Erdős and Schlein were able to do, and many other collaborators. There are also, it's important to mention, there were significant contributions by Terry Tao and Wu. Thank you. Okay, so now there's another class of matrices which can look quite different. There's very sparse matrices, and these arise from random deregular graphs on n vertices. And so you need really different techniques for this, in a sense. This is work that's been done by Bauer-Schmidt, Huang, Knowles, and Yao. And again, if D is large and n is very big, you see in this case you see GOE statistics. So the only randomness is in the graph itself. So you have to put a uniform weight on deregular graphs, which is what they do. So these are the ensembles, I would say, which are reasonably well understood. And I haven't really explained too much about the techniques, except maybe in the case of the Wigner matrices. But now let me go on to more speculative and more interesting cases. These are random band matrices. So I already talked about that. But if we look at D bigger than 2 for D equals 1, we have some understanding. But the minute the dimension goes up above 2, remember these matrices were indexed by a lattice in ZD. They're not just one-dimensional necessarily. And so Wigner-Dyson is expected for, if you fix the width of the band large enough, then you expect to see these Wigner-Dyson statistics for any dimension bigger than or equal to 3, but you don't expect to see it for fixed W for D equals 1, unless you make the width very big, as it was done by Scherbina. So this is a very challenging problem. There's still a lot of activity going on in this area. The other one, which is quite important, is in condensed matter theory, is the random Schrodinger operator. And here you have the Laplacian. This is the Laplacian on the lattice, so it's a nice bounded operator, plus a random potential. And Anderson, Phil Anderson, looked at this model in 1958, and because he was thinking of the random V's as being electrons scattered by random independent impurities, and these impurities are modeled by a random potential. And here I've set the average V squared equal to 1, so it has a unit variance. And here we also expect to see GOE or GUE statistics, depending upon whether I let V to be a complex matrix or not. And but I think it was a long time before one understood that there was a connection between what Phil Anderson was doing and what Dyson and others were looking at. And I think this connection was first made by Gorkov and Eliashberg, and he made the connection between Wigner-Dyson statistics and random Schrodinger, at least at a conjectural level. So this was maybe the first time that was done. So as I said here, Wigner-Dyson statistics are expected for D bigger than or equal to 3. But what's the problem with proving it? Well, the main problem with proving these things is that we need to show that the eigenstates, we need to understand the eigenstates of these large matrices. And in particular, we want to show that they're uniformly spread over the box. And this has been a very hard problem. This is what I call the extended state problem for D bigger than or equal to 3. If you're in 2 dimensions, this is not going to happen. You're going to have localization at some very, very large scale. But in 3 dimensions, this is certainly what's expected. And the time evolution is what's going to be what's called quantum diffusion. It means that the particle will not move in a straight line. It will be bounced around, and it will effectively behave like a Brownian motion. And this is what's called quantum diffusion due to scatterers, and it's the origin of conduction. So that's what I want to say about about random Schrodinger. It's still very much an open problem in the regime of extended states. Now there's another problem. Now this one is these ones I learned about much more recently, so I'm not expert at this. But this I'll start off with this one where I take a Laplacian plus a quasi-periodic potential. Now this is not random. This is a potential you just write down, and here it's written down. Okay, and these vectors here are incommensurate vectors. So these are quasi-periodic potentials in 3 dimensions. I won't talk about what happens in 2 or 1. That's quite different. So these are quasi-periodic crystals, potentials on a lattice. And if you remember Peter talking about quasi crystals that Dyson was interested in. So when I learned about this work, when I learned about this work of this is due to Devacool and Hughes. And Hughes, they were, I think, Hughes is certainly here at the university in physics, and Devacool probably his student. And they observed GUE statistics in the center of the spectrum. And so and not only that, they say this potential, which is very deterministic, they claim it behaves just like a random potential in the middle of the spectrum. There's no difference. So this would be fascinating if one could actually prove something like this. But as far as I can see, this is far beyond our techniques that we can imagine at the moment. But anyway, I think it's interesting because the less randomness we have, the harder the problem becomes, but then becomes maybe somewhat more interesting in terms of its connection to number theory. So this, yeah, okay, thank you. This is a physical statement. This is a numerical calculation. A numerical calculation. That's what I said. That's what I told David Hughes. See, but he's not only claiming that this is true in the middle of the spectrum, but he not only claims that, but he claims that if you look at the mobility edge, it will be like it is for a random potential. Okay. Very, very strange. No, I shared the same skepticism, but I'm somewhat, I think there's a chance it's correct. Let's put it this way. So thank you for the comment there. Now, then the other topic, which was really featured a lot in John's beautiful talk, has to do with unitary matrices coming from the quantization of chaotic maps. So there's this famous Bohigas, Giannoni, Schmidt conjecture, which says that, under suitable circumstances, you'll see the circular unitary ensemble. Now, these are unitary maps, so they're not just Hermitian operators, but they're unitary, but they share some of the same features that we expect to see, of course, in Riemann zeta. So let me show you a particular matrix, which is the quantization of x goes to 2x. That's quite a chaotic system on the interval. It has a Lyapunov exponent of log 2 or something. And then there's a corresponding unitary matrix. I'm not going to try and derive it for you, but it's not difficult to come up with this matrix. So this is a n by n unitary matrix. And you can check it's unitary, it's real. You just multiply it by its adjoint. And if I've got maybe I'm missing a square root of 2 there. Yeah, I think I needed maybe a square root of 2 to make this correct. But anyway, this is the matrix, okay? And for large n, now it's important that n not be 2 to a power. Otherwise, the whole matrix becomes very simple. But as long as n is not equal to 2 to the m, the CUE statistics are observed. So this is yes. So let me see. So maybe I didn't put enough rows in, but you have 1 minus 1, then 0, 0, then 1 minus 1, then you have a bunch of zeros below, and then 1 minus 1. And then there's another line, and below that you have 1, 1, and then 1, 1, 1, and so forth. That it's just repeats. I probably should have put a few more columns and rows in there, but that's what it is. Okay, and so this is something I learned quite recently in discussions with Laura Shaw. She was a graduate student at the university. So this particular type of model is due to Pakonsky and all. They made up these special models for which you could write the matrices down explicitly, and a lot of this work is motivated by Kotos, work of Kotos Smilansky. And also what I found interesting, and I hope to talk to John about it, is this work of Knutsman, Keating, and Piotet. And they use supersymmetric analysis to get the CUE and to understand the corrections to CUE. The corrections are fluctuations about a saddle manifold, which they compute in terms of the dynamics of the underlying dynamical systems, the Lyapunov exponents, the metric entropy, this kind of thing. This is, I think, an extremely interesting paper. And there's earlier work, related work, certainly done by Altland and also Martin Zirnbauer. So I won't say more about this. I'm hoping to learn more about it from John. So how do we get spectral information about a Hamiltonian near an energy level? So this is sort of the basic tool that most of us in random matrix theory use. And it's very simple. I mean, the basic idea is extremely simple, is that we just take the resolvent. We take the Hamiltonian minus E, and now we add an I epsilon. We need to add this I epsilon. It's very important because we want to invert the matrix, and E is going to be in the middle of the spectrum. So if we don't have an I epsilon, we may not have a well-defined inverse. And then you take the trace of that, take the imaginary part and divide by pi. And this will give you the sum of the eigenvalues weighted with this delta function near E. So this trace is just the sum of the eigenvalues minus E. And this delta E, this delta epsilon, sorry, is an approximate delta function. As epsilon gets smaller and smaller, it resolves you at smaller and smaller scales. So the real goal is to understand these Green's functions when epsilon gets extremely small. Typically, 1 over the lattice spacing would be ideal. That's usually too hard, but that's not the lattice spacing. The energy level spacing would be ideal. So this is the well-known delta function. So now what can we do with this if we want to understand a pair correlation? What we'll do is so I have an imaginary part here. With an imaginary part, you have a real and a complex conjugate, which you have to subtract. So what I've written here is a somewhat simplified version of it. I've just written one Green's function, and I have also written its complex conjugate, at a different energy level. These will arise when you compute the imaginary parts. So these are, so this is a somewhat of a simplification, but this contains a lot of the important ingredients. So I will focus on this. So you take, this gives you a delta function at energy E, and you want to calculate the probability that you have an eigenvalue at E prime, and we're going to let epsilon get very, very small. So this E is just represents the average, the randomness. If you have a random Schrodinger, you would average over the random potential. If you don't have any randomness, then this doesn't do you any good as far as I can see. It's very hard to work with this. So, so now the E prime here is just a slight, is a very, very slight change in E. You're just shifting it by a very tiny amount. So that, so this is basically level spacing splits. So we're looking at energies at very, very nearby energies. So that's what you're doing when you're looking at local energy correlations. So this is the expression we'd like to understand. And now let me say how maybe statistical mechanics can reveal some information about this. So I'm going to do a very, very simple example. So I'm going to do a 1-by-1 matrix. It seems simple, too simple, but it's actually a revealing calculation. I'm going to look at the resolvent as I wrote before, and I'm going to write the resolvent with the adjoint. So this is the adjoint, but I shifted the energy a little bit as I want to. Now, I'm going to use a simple identity, which is that if I integrate H minus E, this expression, this is a two-dimensional integral, but it's a Gaussian integral. It's a Gaussian integral which I can compute explicitly. It's just a simple polar coordinate change of variables, if you like. It's a very simple calculation to do. And what I will get when I integrate this just by scaling, if you like, is I will get this reciprocal. I'll get the inverse of this. So you say, well, why would you want to take a nice expression like this and make it more complicated? This is what we do. and it turns out to be useful, as you'll see in a little while. And I do the same thing over here, except I have to do the complex conjugate. So notice that there's a complex conjugate here. So this plus, this minus has become plus, and this minus has also become plus. Excuse me. And this is because I'm looking at the complex conjugate basically of the theorem. But when I do this, and it's important to have the complex conjugate, as I mentioned before. So when I take the average over the randomness, and I suppose that I take the H has a nice normal Gaussian distribution, and I want to take an average over it. Well, this is not a hard calculation. See, the H appears times Z star times Z, and it also appears, oh, I'm sorry. It also appears back here. It also appears as this Z tilde. So what I'll get when I do this integral over H is exactly this expression. The energy has not been changed. And what you'll see now is that you have a hyperbolic symmetry. As you can see, that's hyperbolic symmetry, except that the epsilon and the delta slightly break the symmetry. They slightly break the symmetry. And of course, without them, you can't even, well, without the epsilon, you can't even make sense of these integrals. This epsilon has to be there, otherwise the integrals are ill-defined. Okay, I've been careful to define these integrals so that you have a decaying, a well-defined integral. And that's why I need the complex conjugates to do it. So this is illustrative of why hyperbolic symmetry can enter, and we'll do it in more variables in a minute. But this is the simplest example I can come up with. So now let me just generalize this identity a little bit. So now we're going to put an n by n matrix. So I'm going to make it Hermitian, and now my z's are not just are not just not one variable. I have to have n variables because I have n matrix, n by n matrix. So so now I write the same thing down, except that I have a dot product here. It should be there, and I do the integral. This is also a Gaussian integral. One can do it explicitly, and of course, what you get is the determinant. You get the determinant of the Hamiltonian minus the energy inverse. Okay. You get the inverse. You get the inverse of the determinant. So so if you do this in one variable, of course, you know how to do it, and it works the same way. You can just diagonalize. So this is not a deep identity. It's very well known. It even works in cases where you don't have self-adjointness of the matrix. But anyway, that's not so important. It's a very useful formula, widely used. And so now if I want to go from the determinant to the trace, I just take the ratio of determinants, and I take the derivative, and that will give me the Green's function. So so that's all. It's just the logarithmic derivative of the Green's function. So now but when I do that, generally speaking, I've got to get a determinant with a plus power too. Otherwise, I can't get a hold of Green's functions in a natural way. So this is done with Grassmann integration. So these are things that I know most of you are not so familiar with, but it's a very similar formula, except these are non-commuting variables. These are anti-commute, in fact. They're like dx, dy, and these are like wedge products, if you like to think of them that way. So you can think of the size and psi bars as being dx and dy, and the wedge product means they anti-commute. And so when you do this integral, instead of getting the determinant inverse, I get the determinant. So this is a very useful formula. And when you put the two together, you can compute Green's functions and look at ratios of determinants. And ratios of determinants are, of course, Green's functions by Cramer's rule. So these are the tools that we make use of. And so I won't say too much about this, except I will come back to it in a moment, but not in such a serious way. So now I'm going to do a calculation here, which is, I think, fairly helpful. At least if I do it slowly enough, perhaps you might even be able to follow some of the details. So what I'm going to do is to compute a determinant of a random band matrix and relate it to a classical spin system, what's called the Heisenberg spin models. So let me just say what I want to do here. So we're going to be in one dimension, but it won't matter so much what dimension we're in, except for proofs. So we're going to have the JIJs, which are the off-diagonal, tells you how the off-diagonal elements of the band matrix behave. And we're going to take a specific form of it, which is called the Kotz potential. It decays if I minus j is much larger than W, and this is the normalization. So don't worry too much about this. This is just a way of enforcing a band at width W. But it's a very convenient one. Now, what I'm going to do is to explain how to compute a determinant of the matrix, the band matrix. By the way, I'm in a box of size n. J and k run from 0 to n. That's important to say. So I have finite determinants, but I'm going to let n get very big. And so we take h minus e plus the delta prime, and h minus e minus delta prime. So I have two different energy levels split by a small amount. And I want to understand how the determinant varies with delta. And so I call this z delta. And this delta is split by this delta is normalized by essentially 1 upon m times the density of states. And now this is the theorem of Scherbina, which says the following, that if I look at Zn, and I should have a Zn down for Z0 there. But if I look at the ratios of these determinants, average determinants, this approaches sine delta when W is bigger than n to the half. It's very much like the theorem that I mentioned that in random band matrices, except here we're just looking at the determinant, nothing more. So this is what happens when W is much bigger than n to the half. When W is much less than n to the half, this ratio goes to 1. So I'm missing a subscript z of 0 sub n, but that's all that's missing there, I think. So that's what happens. You can actually calculate in this random band ensemble this limit, and it's in a sense universal. It's not quite as universal for reasons I won't go into, but this these kinds of calculations are illustrative of how you can use statistical mechanics. So that's what I want to get into. So this is the theorem. It should also hold not just in 1D. I expect it to hold in 3D for these band matrices, and without even any conditions on W. And 3D should be valid anyway. One corresponds to just the fact that it's my normalization here. So when I take, I have a delta here, but if I take delta equal to 0, it's just a normalization so that I have something. Otherwise, this guy grows too big. It's too big. So I want to look at a ratio of these partition functions, if you like. It's a ratio of partition functions. So this corresponds to no shift in the energy. And here I have a shift, a small shift to the right and a small shift to the left. Yeah. And so this goes to 1, and we'll see, which is, I think, quite nice, very elegant, that when you study these matrices, you think, well, this is determinant. This is a Schrodinger operator, but we'll see in a little bit that is really quite equivalent to understanding what's called a classical Heisenberg model with an SU2 symmetry. Yeah. Yes. What's that? E. No, you're looking at energy levels near E. So I'm looking in a neighborhood. So when you fix E, and then you look in a little neighborhood of E. It doesn't depend. No. You see, there's a normalization there that depends on rho of E. That's where it is. Yeah, except for that. It's universal, right? By the way, the statement, of course, is easily calculated if you have a GUE ensemble, but here it's true for the band. And if you went to higher dimensions, it should be true, not proved, in 3 dimensions without any condition on the width of the band, just to be bigger than 2 or something like that. So I'll mention that later. Yeah, any other questions? That's the statement of the theorem, and one can look at, maybe it might be interesting to look at higher moments. You can look at more correlations, more products of determinants, and but I think Tanya has looked at that, but I'm not reporting on that today. Okay, so what is the idea of the proof? Well, this is where statistical mechanics comes in. There's a saddle manifold, and then you have to control fluctuations. So here, let me just say a little bit how this goes. So I'll have plenty of time to explain this. So because I'm running ahead of schedule. So here's an explicit expression for this Zn delta. So here it was before, the product of determinants, and now I'm going to write it out. And there's a little algebra to be done here, but it's not very difficult. That you can write these products of determinants in the following form. This is the weight. This is my Gaussian weight. And by the way, these xj's, I have to start off by saying, these xj's are 2 by 2 Hermitian matrices. They're not they're not scalars. They're 2 by 2 Hermitian matrices because I have two determinants basically. And then we have a product of the xj's minus e, product of xj's minus e with a shift. So it looks the same, except now I have 2 by 2 matrices, and that's all I have to do. And now I try to find out what the saddle of this is. So this is a big integral. I have n factors. This runs, j runs from 1 to n, and I'm going to look at this thing for large N and large W. And but the thing to do, what physicists would do, mathematicians also do it, is to find out where the saddle point, where is the stationary point of this integral. So you can compute this by taking the log of the determinants in terms of traces, and then taking the derivative, setting it to 0, and you'll find that there's a very nice saddle which is independent of J, and it's just given by a matrix, which is I E over 2, which is times the identity matrix, which is a 2 by 2 matrix, and then we have this factor, which is like a density of states, times this factor here, which is just the Pauli spin matrix. So that is the saddle. I won't do the calculation for you, not extremely revealing anyway, but this is the saddle. And now you have to say, well, okay, this is my saddle point. To what extent does it govern this big integral? That's really the question. So let's first think about what happens when we look at the saddle. So for delta equals 0, we can, so that means that these are both 0. You'll see that this integral has an invariance under an arbitrary unitary transformation, spatially independent, but arbitrary unit. So this is also a saddle. So that means we don't just have one saddle point, we have a whole manifold of saddles that we have to understand. And then we have to understand maybe some fluctuations about the saddle manifold. And so this is really effectively what Tanya did in her work. So if you approximate xj by this factor, so this is a unitary times this Pauli spin matrix. The orbit of this is really just a sphere. And when you write out the new effective model that you have, is what's called the classical Heisenberg model. You have a gradient of the spins, which now lie on the sphere, and you're integrating over the spins. And that's your partition function. So this is how you go from something which looks very much quantum mechanical or random matrix type to something which is really quite classical. The classical Heisenberg model is well studied and not as understood as it should be in higher dimensions, but we know quite a bit. We know about phase transitions and so forth. So this is the connection I was hoping to make in terms of statistical mechanics. And the point is that in one dimension, the spins are aligned, provided that the beta, which is the inverse temperature, which beta here, by the way, is just this factor here. So it's the width squared. So let me go back, show you. Yeah, this W squared is the only thing that survives, times this factor. And okay, let me see. Yes. All right. So yeah. So now, so I've tried to explain a little bit about the saddle point, but as I said, there are corrections to it. So this is only valid if the width is wide enough. Okay. So in 1D, the spins are aligned, provided this W squared is much larger. Oh, I'm sorry. Much larger than N. You have to have that. So in general, there are corrections, which I'm not, don't have really time to explain, but these are corrections which have been derived by physicists. They're not rigorous for the most part, but in some cases, one could make them rigorous, presumably. And there are corrections to the saddle. There are fluctuations away from the saddle, and they were given by Kravtsov and Mirlin, and they are of the form 1 over beta times n to the d over 2. So they have very precise corrections, by the way, to the pair correlation, and they're not universal. They depend upon the shape and the geometry. that you're working in. But they have very precise corrections. And that's one of the advantages of using statistical mechanics, that you can get these things. But notice that in dimension 3, as n gets large, this quantity gets very, very small. So your corrections to the saddle are even smaller as you go up in dimension. In 3D, there are corrections of n to the -1 for n large, and the spins are aligned at all temperatures. So the universality of Wigner-Dyson is really quite related to the what's called the low temperature phase of classical spin systems. It's not isomorphic, but it's quite closely connected. So far, I haven't really told you too much about supersymmetry per se, partly because apart from one dimension, it's a very difficult formalism to work with mathematically. Although it's very beautiful, you can see many things at a formal level, but proving things is generally speaking still out of range in higher dimensions. But there's a simple model. So this is my last slide. There's a symmetry breaking for a simpler 3D supersymmetric model, which we worked out a few years ago with Martin Zirnbauer and Margherita Di Sartori. And this is a model which is not nearly as complicated, but still quite rich. It has a phase transition in 3 dimensions. And for beta small, we'll get a localization factor. But for beta large, which is what we expect to be the most interesting regime, you'll see the quantum diffusion I referred to when I was referring to the quantum diffusion for the Anderson model, for the random Schrodinger. So, and here's the diffusion can be really written as a Green's function of the Laplacian. So you have a change of form. You have a Laplacian with a random potential or a Schrodinger evolution, but that Schrodinger evolution doesn't behave like a wave, behave more like a heat equation. And that's what we see in this formalism. So this turns out also to be equivalent to a vertex reinforced random jump process, which was introduced by Wendel and Werner. So here we go from really questions about zeros of Riemann zeta to just jump processes in 3 dimensions or in 2 dimensions. And so this is a kind of thing that I would say, these conjectures about Riemann zeta zeros have really inspired a lot of this work, and it has inspired certainly the things I've talked about, and also all the way down to things like vertex reinforced jump processes, which are a simplification of these random Schrodinger models. So with that, I will stop, and thank you very much.
I'll let you.
Okay, go ahead. Yeah, you have to speak up a little more.
The 1 by 1 matrix model.
Oh yeah, the 1 by 1. Yeah, everybody looks at it. So let me come back to that. Let me come back to the complex. Let me come back to the 1 by 1, because that is, okay, here we are. Yes.
And then
So this is yes, one has one. I could put a minus delta in there too. I was lazy. I didn't do that. The delta will depend upon, the delta are going to be very, very small. Here is just you shouldn't take this too seriously. This is just an example of how you look at Green's functions, how you can try to understand Green's functions through this kind of dual representation where you integrate over complex variables. So this is just an identity, right? And so I'm illustrating it because in the previous slide, I did have 2 different, these E and E prime were different by some small amount, right? So I put that in there too, just to illustrate that I could do that without any problem. But the point about that is, if I could say, the point about that is that this delta and the epsilon, they both break the hyperbolic symmetry. You see, because if you look at it there, or even if I put it, it doesn't matter where I put it, they break the hyperbolic symmetry. So you have to understand, even though they're very tiny, you have to understand how the hyperbolic manifold, which will be running around the system in larger situations, will affect these tiny symmetry breaking pieces. So it's yeah, I'm not sure I've answered your question, but what was I trying to answer? Did I answer your question? Yeah. So the integrals are well defined. It's an exact formula, but if delta is very small, epsilon is very small, you're going to break this hyperbolic symmetry, and you have to understand how that happens in higher dimensions. Sorry. Oh, after this, okay. Oh, yes. You want to know how I got to that step. That's okay. So you want to know how I got from this step here where I get where I have the, I can use this pointer. No, maybe I can't. Oh, there we go. So you want to know how I got from this to this one. So these X's are just 2 by 2 matrices. Before they were, big matrices, right? Now they're just 2 by 2. But don't forget we had a product here, n-fold product. So this is not a totally trivial, but this is just an identity. I won't try and do it here, but this is just a little bit of algebra. You have to work with the Grassmann variables a tiny bit. It's very helpful to do that. But in the end, you don't have them. There are no Grassmann variables here. They're determinants, but the Grassmann variables don't appear. And so this is just an exact expression, modulo factors of pi and I probably, which I may have messed up. But this is basically what you have. And now you have an integral over many, many variables, and you have you have parameters, and you want to understand how this behaves. And so the first thing you do if you have an integral is you say, well, if I got some large parameters, I got large volume, or I got large W, let me look for a saddle point, or look for a saddle manifold, which is what we'll have here. And here is what you get when you do this. Actually, there are two. I didn't go into this, but there are two of them, but the other one is subdominant. And so you have to look carefully at these things. This is the one that's important. This is the one that's relevant. And so your X saddle, this is the saddle, is independent of J. Okay. And then you can say, well, okay, why does that tell me anything? That's just a saddle. So then you have to go and work hard to see how you can control fluctuations about the saddle. And so that's of course what Schrodinger does. But she can only control the fluctuations if the width is big enough. So the width has to be bigger than n. Yeah.
So if the width is big, very big, so that we're really back to.
We're back to, right, exactly.
And it seems that she has a derivation of the local spacing statistics for the Gaussian ensemble, which does not use a Poisson polynomial.
This is not a thought. She uses the supersymmetry method.
Right, but
yeah.
it's rigorous.
Oh, absolutely rigorous. Absolutely rigorous. So that's important to point out.
I mean, John mentioned this lecture of Wigner from 1967, where he couldn't do this. He was just trying to do that.
Right.
And Godin solved that with the Poisson polynomial.
So this is very different technique.
But it is a rigorous.
Absolutely rigorous derivation.
And quite different to the work of Yao et al.,
Yeah.
which all say that it's universal, but they don't recompute anything.
This computes it from first principles. It's different because it's really.
What bothers me.
Yes.
And it's rigorous.
Yes.
Usually when you have saddle point method with the number of integrands.
Right.
I'm familiar with the saddle point method in fixed dimension, and then I look for critical points.
Right.
But you've got n growing with it.
Correct.
Well, but you say
Correct.
it's rigorous.
It is. One way to check, one way to understand the limits of how valid it is to look at the fluctuations away from the saddle. These are the normal fluctuations, which are Gaussian fluctuations because they're quadratic. And then you can see whether how important they are. And no, it doesn't, it's not important.
So you're not going to give a new proof of Yala's work.
You might, in principle, you can. In principle, you can, yes. In principle, you can. I'm not going to do it for plus or minus ones, but I'm just saying it's the fact that the elements are Gaussian is not relevant here. It's not relevant. The fact that you, yeah.
I understand at the formal level,
Yeah.
that's true, but rigorous level, that's.
Well, at a rigorous level, it's very helpful to have Gaussian things, but it's not essential. It's not, yeah.
Okay.
Yeah, that's what I would say about that. Yeah. So for example, I mean, this work that I mentioned right here about the corrections to the satellites due to process of Mirror, this is not rigorous, but it's very precise. It will tell you exactly what your corrections to it is, and it's just really considering the Gaussian fluctuations, and their theories are not Gaussian, not at all. These are very different theories.
It gives the right answer.
Yeah, it gives the right answer. And it's just, sometimes you can control it, and unfortunately we can't.
The
Yeah.
question is, where did sine pi x of a pi x came from? And in this calculation, it comes from a saddle.
Yeah.
And that's something very interesting.
Yeah, that's right. Corrections.
If not, then I think it is lunchtime.
Yeah.
Let's thank Tom Spencer for running this.